we'll just get started. Welcome, everyone. We are in number 7, lesson 7, week 7, whatever you want to call it. We're going to have somewhat of that collaborative filtering discussion from chapter 6. Daniel will present that. I'll let Anya present hers on the chapter 8 piece on the random forest model. Chapter 9, sorry. I keep looking at my little thing and it says lesson 8 in my
yeah, we're a little mismatched.
Yeah. And then I wanted to present the Excel one if you wanted to go back and forth. So if we can switch presenters, that's fine. I guess Daniel, you will be up first. Is that okay?
Yeah, no problem.
Okay, so I will make you co-host.
Wonderful. Let's see. Is that the right thing? Yes. All right, so everyone see my screen and hear me all right and everything?
Yes.
Yes.
Great. So as with last week, this doesn't really differ from the book too much. I basically applied the process of chapter 8, the collaborative filtering deep dive, to a different data set. So I'm just going to quickly walk through that, point out a few observations along the way, point out the things that were a little bit different. So the data set that I used is the book crossing data set, which is sort of a benchmark data set for collaborative filtering problems. If you look it up, I think I found it by Googling collaborative filtering data sets. So that's where that came from. Let's see. The Zoom drop down is blocking my ability to click on the tab, but the website that it comes from looks like this. I just downloaded the Csv Dump, which has a few CSV files for users, books, and book ratings. I obtained that through the same process as we do with sort of the prepackaged data sets that Fast.ai uses, but I passed it this link. So I use the untar data function. One note as we get started, if you want to avoid printing, so I did this on Colab, so I have to pip install upgrade Fast.ai. And if you want to avoid that printing out a whole bunch of lines of stuff that you don't need to see, you can put this little capture flag, and all of that will be silenced. So just a small formatting note. Yeah, imported the libraries, downloaded the data. One slight difference in this case is that this unzipped the 3 CSV files directly into the .fastai/data directory, where typically with the prepackaged ones, so like the MNIST downloaded from Fast.ai, it'll create a new directory. So when I was referring to that with the Pandas read CSV function, I had to look at path.parent. So just a small thing to be prepared for if you look into this data set. So as with chapter 8, the 2 things that I was interested in, one is the file with the ratings themselves, and one is the file with the names. In the ratings file, the books are referred to by their ISBN numbers, which for my purposes and probably your purposes are not very interpretable. I don't know books by their ISBN numbers. So I grabbed both of those. It took a bit of messing around with the formatting. I had to get the encoding right, had to make sure to specify the separator characters, the quote characters, because in a lot of cases you had titles that had semicolons, titles that had single quotes or double quotes. So that just took a bit of trial and error. And there were escape characters throughout, so I had to specify that too. This was actually probably the most time-consuming part of the process, was just trial and error, getting all of the formatting figured out. Yeah, so this was a semicolon separated file. Let's see. Yeah, and then we can look at the head of the ratings file. And just like with the movie lens, we have one column of user IDs one column of ISBN numbers, which are the books, and then a rating. And you can see just from looking at the first 5 that we have a rating of 0 and a rating of 6. So we know this isn't the 1 to 5 scale. I looked into it, it's 0 to 10. Another thing to note here is the shape of the ratings file. We have more than 1.1 million ratings, so this is quite a bit bigger than what we were working with the movie lens data. I probably should have just taken a subset of this based on the most popular entries, but I muddled through with the whole data set. Definitely took a lot of time and pushed Colab past its limits, but I got it to work on my GCP VM. So yeah, we have more than 100,000 unique users, more than 340,000 unique books, and 11 ratings. I should note that after I ran all of this, I did a little bit more reading, and apparently 0 has a special meaning in this. It referred to it as an implicit rating, something where they had information that the user obtained or read the book but didn't rate it. Didn't figure out exactly what that meant, probably should have excluded it, still got some pretty decent results with it. So another thing to be mindful of if you decide to try to replicate this. So the next step was to make this process interpretable to some extent, and that meant getting the book titles. Recall up here, one of the files that I downloaded was book names or bxbooks.csv. So we'll just take a look at that to start with. I only grabbed a couple or a few of the columns. I made a new column called title author, where I just combined the title and the author, put the author in parentheses because there were quite a few cases where there are many books by the same title with different authors. So I wanted to make them unique. So now we have this sort of lookup table of the ISBN and the author and title combination. And so we make a final books data set that merges book names with our book ratings by title on the ISBN number. So here you can see the first 5 entries are all the same book, same title, same ISBN, and then different users giving different ratings. Yeah, so any questions at this point before I keep on going ahead? All right. So, sorry, excuse me. Next step is to prepare the data loaders object. This is the same process as in chapter 8. I made a couple of the steps a little bit more explicit. It wasn't clear to me from chapter 8 how the data loaders knew which was the user, which was the rating, which was the item. They just used it based on positional arguments. So I believe it was that user is in the first position, item is in the second position, and rating is in the third. I, again, just made it explicit, used the keyword arguments here. Same batch size. I don't know if changing the batch size would have done anything, especially with such a large data set. Kept it the same. Set the seed, show a batch, and we have very simply our user ID, the book titles, and the ratings. And you can see that there are a lot of these 0 implicit ratings, so it probably would make quite a difference if I cut those and treated those differently. So we will fit the first kind of model. I didn't write the models from scratch in this case, as was done in chapter 8. I just used the built-in methods. So the collab learner function, took that, did the same 50 factors. Y range, I did 0 to 10.5 instead of 5.5, given the wider scale. I did the learning rate find, and actually I had a pretty large learning rate suggested. So I went with about a 0.1. I used smaller learning rates in other runs, and it was pretty similar. And you can see how this worked as far as validation loss. It went down a bit over the course of the time. And I guess this brings me to my first sort of discussion point, which is how to interpret the validation loss. I'm thinking, because it's the MSE loss flat, that the square root of that loss would be in the scale of the original ratings. Can anyone confirm that? It seems to match up with what I would expect here. This would be a loss of like 3.5, or this would represent like an average error of 3.5 from the ratings on the 10-point scale. I don't know if anybody else looked into that or thought about it. But I don't know, that was my assumption. Yeah, just going through the other questions I had over this time. Again, how does it know which is the user, which is the item? It assumes user in first position, item in second, rating in third. Just look at the documentation for that one. I ran this without looking at the size, and it took a very long time compared to the other one. So obviously, number of observations is an order of magnitude larger, so that made this take a lot longer. I know when we made this from scratch in chapter 8, I think that the user IDs were more of an index. I think that they started from 1, maybe. I can skip that one. I don't really have much of anything interesting to say about that. The biggest thing that I was not sure of as I was working through this was the process for hyperparameter tuning in Fast.ai. Anya, I think that you mentioned last week that you're sort of more familiar with like the scikit-learn pipeline type approach where you do a grid search or something like that. That's also sort of the world that I've worked in with this stuff before. So I had a lot of questions about tuning, like the weight decay, the learning rate, number of epochs, things like that. It seems like there's a lot of opportunity to tweak those things, but also given the computational time and everything, it's a bit more of a process than I got into. So I followed the process of just looking at the bias terms to figure out sort of what were the most popular books. Most of them came as no surprise. The Harry Potter books, the Little Prince, saw that, I was like, yeah, that makes intuitive sense. But then the other one was Free by Paul Vincent, which has like 3 Amazon reviews. Didn't make a lot of sense. Though I did actually find on Kaggle, somebody did an exploratory data analysis, and for whatever reason in that data set, this was one of the most rated books and had a fairly high average review. So I guess that's a cautionary tale to figure out how well your data aligns with the real world before running with it.
He bought his likes, maybe?
What was that?
He bought his likes, maybe?
Yeah, who knows? Yeah, on Book Crossing, that's where I usually go to buy likes and sell books. So next, I went through this process again using the use NN equals true argument. I did the get embed size thing first, and they both ended up at 600, which makes me wonder if that's considered an upper limit, given the size of both the list of users and list of titles in the training set. Otherwise, everything else I treated the same. I treated layers the same as in the chapter 8 example. Again, another thing that I would be interested in knowing how to thoughtfully vary. Looked at the suggested learning rate. Went with a little bit lower of 1 here. And if we look at the validation loss here, we can see that, first of all, right from the get-go, it's quite a bit lower than when we started here. The lowest we got to was 13 here. And even after 1 epoch, we were down to 11.9. But by the time we got to our 5th epoch, we had a training loss of 9.4 and a validation loss of 11.9. And that validation loss of 11.9 is higher than the loss of the prior epoch. So it looks like we got into some overfitting territory. So I ran this again with 4 epochs, and because nothing goes exactly how you want it to go, the same thing happened jumping from epoch 3 to epoch 4. where the training loss dropped pretty significantly and the validation loss went up. So that was exciting. One thing to note, given the size of the data set, this took more than 50 minutes to run, more than 10 minutes per epoch. Same thing here. And if we look at the plot loss here, you can see that huge drop in the training loss. I don't know what accounts for that like very precipitous drop after a certain number of epochs, but it's interesting, I guess. And that pretty much brings us to the end of what I wanted to show. When I tried to do the book bias rating thing again, I got a bunch of errors. Ignore this, I was trying to tweak it and figure out what was going wrong, but I ran out of the time and energy to do it. I exported the model with the hopes of trying to figure it out in the future, but I don't have anything to show on that now. This is what I got for the error. Embedding NN object has no attribute I bias. So I'm assuming there's a different way to get that data. So again, at the end of all of this, the biggest questions that I have, we've seen a lot of hyperparameters over the course of this, and it would be interesting to know how to thoughtfully tune those to make this a little bit better. Also would still like to get confirmation of whether I'm interpreting the validation loss correctly or if I should define a metric. And also if there's any clear explanation for this pretty sudden and significant drop in training loss. But that's what I got. Thanks for listening.
Are those each epoch, like the where it drops? Like see up how above there's like 1, 2, 3, and then you can like almost see a shift.
Yes, it looks, that would be my guess because they're all about the same size, and then this last one is just very dramatic.
I mean, my first thought would be that that's the point where your model began to memorize the data set.
Mm-hmm.
But with that many points, with that much data, I wouldn't expect a few epochs to be able to memorize it, you know?
Yeah, that's kind of what I thought too. And for it to have occurred kind of so sharply at the new epoch.
Does it make a big change when the epochs end? Like, to the calculations?
I guess, I mean, it would be after each, well.
Or does it do it on the fly? I don't know.
I mean, it looks like there's a step function at each of the epoch.
Yeah, it really does.
Does it adjust the learning rate per epoch? Because remember, we were looking at adjusting learning rates, and maybe that makes a difference.
I think I looked at the learning rate code, and I do believe that that's how it does it. So that's
maybe it's a better rate.
Yeah, it's probably a good theory. But it would make it, I think, a lower learning rate over the course of the time. So it still kind of surprises me that it would drop like that.
Yeah,
and there definitely seems to be an element of randomness too, because again, after the first time I did it, it kind of had that big drop after the 4th epoch, and then this time after reinitializing the model, it was after the 3rd epoch.
Yeah, but remember when Jeremy cautioned that you should always start at the 1st epoch, you shouldn't start the model again. Or you shouldn't take the model, like of your first model, you wouldn't take that 4th one, because the learning rate changes over the course of the epochs you tell it to.
Yeah.
So to me, it kind of makes sense that getting to that you see the same trend, right? Because it's still that the last learning rate is still the same.
That's a good point. Yeah. So this definitely leads me to thinking that the learning rate has something to do with that. So I wonder if I do this again and I do that thing that we learned last week of giving it a slice for a maximum and minimum learning rate, maybe with the minimum learning rate a little bit higher than whatever it would calculate, that might work better.
Yeah, the other thing I'm confused on why the validation loss is that large. And I understand what you're saying up there. I haven't worked out the math in my head to agree with you yet. But like the span of the book examples was, I don't remember if it was 0 to 5 or 1 to 5. I think it was 0 to 5. But its validation loss was, 0.9. So it definitely wasn't larger than, I don't know, that confuses me a little.
So I think that the inclusion of those zeros, the implicit reviews that I didn't account for, probably has a big part to play in that. If you just like,
I agree with that.
So yeah, so first of all, I think that there are a lot of them, just from looking at the high level summaries. I read about there being this implicit review thing like 5 minutes before we hopped on the call here. So I've really not investigated this very much. But assuming that those present a pretty big issue, you can imagine that if the average rating is like a 5 or something, then each one of those zeros is going to represent like a 5-point error, basically. And
right, and that might actually be what's causing that weird behavior that we were just talking about too.
Yeah,
like if it memorized all the zeros.
Mm-hmm. Yeah, that makes sense. Like if there is something, especially if there's something kind of fundamentally different about those, I don't know, about the latent factors associated with the zeros or something.
But why would it wait until that epoch to start memorizing the zeros?
Sorry, could you repeat that?
Yes. In the conversation, in the discussion, I missed why would it wait until that epoch to start memorizing or overfitting, memorizing the zeros? Why would it not start doing it up front?
It has to make a certain number of passes before it can memorize the set. But what I'm looking at is the drop in the training loss is significant compared to where it was. And then the worsening of the validation loss, right, is big. So you're getting better, worse on validation, but you're getting slightly better, and then a lot better on that last training loss. So that's why I was thinking along that. I don't have the answer.
Yeah, no, that's fair. Your point is that right where the third and fourth cross, the validation loss dips up. Goes up. There's a bit of a dent point. Yeah. Okay.
Yeah, it goes up, and the training loss gets much better compared to the previous steps.
Yeah.
Yeah, but like I agree with Daniel that I think if you take root of mean of MSE, then it's gonna be on the scale of ratings, which is between 0 and 10, right? And then that loss is like the loss change is very insignificant because it's still very close to 3 point something, right? Like all of validation losses is 3 point something then.
Yeah, in the original scale.
Yeah. So yeah, that's the trick when you like, it's really hard to understand deep learning models and interpret them. It would be nice to dig in or have someone to give us the answer.
Well, in retrospect, I'm really glad that this ended up having this sort of weird behavior. I think that this was a useful conversation for me.
Correct.
Well, what'll be nice is if you get a chance to rerun it, removing all those zero ratings.
Mm-hmm.
And one, your training time is going to go way down because there's so many of them. And then two, we'll be able to look at, this again.
Mm-hmm.
Yeah, and publish it so we can review it.
We'll do.
And the other conclusion I'm thinking about this is the point where they cross the training and the validation curve is probably the optimal loss or the accuracy value, right?
Yeah.
So until something fundamental, like removal of zeros or something fundamental is done in pre-processing and rerunning the whole thing, that is really the point of accepting this model.
Mm-hmm.
Yep, I agree. Though again, I can't even really get to that point on a full run without figuring out the learning rate issue. Because it seems like there is just some fundamental shift when it gets to the final learning rate.
Very nice.
All right, well, thank you. And I'll put that on the GitHub, so you can all feel free to take a look.
Thank you.
Thanks.
And now, Anja, thank you, presenter, co-host.
I'm going next.
Yeah.
All right. All right, so I'm gonna share my screen. And again, a disclaimer that, you know, I'm trying different things. So I read the chapter, I watched the videos. It was a lot of learning. I'm very impressed with how Jeremy covered random forest, because he gives us a lot of background before he starts moving to deep learning. So that was pretty cool. And so what I decided to do, I didn't think I would have time to actually do anything, but I did find time, I guess because I skipped water skiing. I was gonna go water skiing, but I didn't, just for the love of deep learning. And I guess I'm gonna show you what I did. All right, so I ran the clean code and I got it to work and it made sense. And now I wanted to try something different. So I chose another data set from Kaggle. It's a way smaller data set. It's only 6,000 records with 14 fields. So the bulldozer data set was about 400,000 records with 50 fields. So this is significantly smaller, and I have to say that I do know that it's not a good candidate for deep learning, because deep learning is very good for large data sets with a lot of features, so humans don't have to do the analysis. But this is a good data set for me because my goal for this was to learn how to apply deep learning and how to compare random forest to deep learning. And the less columns, the easier, because, as a human, I can comprehend 14 columns and 50 would be 3 times as much work, 4 times. So that's why this was my strategy. So this is not a mistake that, I don't understand like when and how to apply deep learning. So this data set comes in train and test CSVs, and test doesn't have answers, so it's not usable for learning because I could only submit my model to the competition, but I couldn't verify the results. So I will only be working with trained data, and I will use it for training and validation. So the columns here are pretty basic. There's a ID number, like name of the car, location, year, there is power, number of seats, new price, and I guess it's a data set from India, so it's in local currency, and a price, I guess, once it sells, in like when it really sells. So I looked at the values, and this is our target variable, which is a numeric value, which is what I want for regression. And some values that I saw, like power and a engine and mileage. And mileage it's like in the US that's miles per gallon, and in India that's kilometers per liter. So this, for example, power, because it's a string, so it's not a numeric value. So I decided to make them numeric value because, you know, like horsepower and mileage, that's all numeric things. And in this data set, they came as strings. So I did add, let me see. Yeah, I did convert those to numeric values. I didn't get rid of the original fields. I left them as is. I just added numeric values for mileage, engine, power, and the price, because as you saw, price was in local currency with this currency name. So that's the difference between this data set. I did some initial pre-processing as a human because I understand the machines like numbers. So I decided to see if they like my numbers, or they're okay with me not converting things. So our dependent variable is price. This is my data set that I'm gonna ready to model. So you see my conversions here, they're all floating numbers. Make sense so far? Any questions? All right.
That makes sense.
Okay. And oh yeah, I was gonna say, RK, this is this is probably, you will see errors because I don't understand cars and you do. So so maybe.
I mean, it looks good so far. I mean, I think it was really smart of you to pick a more familiar data set than, I mean, I don't know anything about bulldozers, so
correct.
Like the 50 variables that he had there, I didn't know what half of those things meant, but all of these I know what they mean.
Exactly.
So it's like, you know, and then the conversion to numbers, I agree with that too. I think that's really smart.
Yeah. So yeah, so everything you see with num at the end, that's my additional things. All right, so then I am ready to model, and we start with a simple decision tree. And you know, I looked at the at the years. So we have cars from 1998 to 2019. This is an important concept in Fast.ai. So under the hood, this is Pandas data frame, but Fast.ai made it very convenient by creating Tabular Proc and Tabular Pandas. So it makes easy for us to categorize and fill missing categories. Then in the bulldozer example, there was some time trend. So it was a time series data. Here, there is no time trend, there is no dates. So me splitting by the year was not necessary. So I had to do split randomly. So I split the entire data set, which is 6,000 columns, randomly. And this is the size of my train versus my validation set. Then I did what the book does. I have to tell the pandas what's continuous, what's categorical. You can see that all of these things are continuous, numeric, and the rest is categorical. So I created my tabular pandas data set, and this is what it looks like. So if we look at how this is interpretable by humans, so that's what we see, and this is what we send to the algorithm. Under the hood, it's all numbers. So, you know, even location and names, it's all converted to numbers. That's what Categorify does. And there was some, oh yeah, I forgot to mention, guys. There is, remember he talks about ordinal categories where order matters. So in my early part of the code, I made it in order of that owner type can be first time owner, second, third, fourth, and above. So I did it earlier on. Over here, I looked at owner types and I just made them in order, just to see if that makes a difference, because when the order exists, it matters how you categorify. If order doesn't exist, then it doesn't matter. All right, so I think that was, yeah, that was where, so I'm saving this so we can reuse it. Then I'm creating a decision tree, and this is just like in the book, we limit it to 4 nodes. And this is a pretty good visualization. You can follow, this is our base value where the average price is 122, let's say dollars. It's not dollars, but let's call it dollars. And you have this true versus false. If it's less than this, then you don't need any more splits. If it's more, then we're splitting more. So we're arriving to this 4 leaves. And sorry you can't see it here because of the limitations, but I can show you what it looks like. So it's the same, just more graphical. You can arrive to more detail. You can see distributions. You can see how decision trees split the space into, like linear models split the space by a line or a hyperplane. Decision trees use vertical and horizontal lines to split your data. So it's the same as the other visualization, it's just with more detail. Okay, so, and after this, just like in the book, we look at the training RMSE and it's 0 because everything is perfect. And of course it's not. We look at the validation, it's higher. So because it's RMSE, I assume it's in the same currency. So it's $6.7. But if we compare number of leaves versus number of records, they're almost the same, meaning we overfitted the data set. And we applied the sample leaf equals 25. So we made sure that each leaf ends by having at least 25 examples. And the training loss went up, which is good because we don't want it to be 0. And the validation loss went down to 532. So that's one decision tree. And our number of leaves is 150, way less than this 4,500. All right, so random forest is a bunch of trees, bunch of randomized trees. I won't go into detail because that's a topic of its own. And I have to say, Jeremy does an impeccable job covering random forests because I used them before and I understand them much better now. And I actually want to go back to work and apply it, but I don't think management will allow me to spend time on the previous model. We'll see. But basically, we do random forest. We have 40 trees. Here, we are not playing with hyperparameters. We're just specifying 40 instead of saying the range of like 40, 50, 60. So our RMSE is better. So our validation loss went down to 4.82, and here was 5.32. So remember these numbers, 532, 4.82, because that's what we're comparing. And this is the graph of how the validation loss keeps improving. So by becoming smaller and smaller with number of estimators, which is number of trees, it's becoming smaller and smaller. So that's a good pattern. Out of bag error, that's where it's an awesome shortcut that Jeremy pointed out, that because we are using randomized trees, we can use those trees not used in training just to see an error inside. So the error is 4.0, which is, I don't know how to judge. Is it much, like 4.82 versus 4.0? Is it much better, or like is it decent? So it's not a super large difference, but it's significant, because it's, you know, it's significant percentage. But it's nice to know that we can do out of bag error to compare the results. And the model interpretation, so he goes into that, which is pretty good. You can, instead of looking at the RMSE, we can look at standard deviation, and you could see that these numbers are quite different. Like 7.62 is way bigger than 0.95. So that gives you kind of an idea how confident we are. Then we look at feature importances. This is the table, and this is the graph. The graph is easier to look at. And owner type and owner type category, this is where I made it ordinal value versus that's where it came in. And they seem very insignificant, and we will be getting rid of features that are not very important. What seems to be important is the numeric values, which is the power, engine, then year, transmission, power. Again, this is the original field, because so far I am using both of them. And then kilometers driven. So after that, you see this kind of elbow shape where after this, these contribute less to the model. And before I get rid of unimportant features, I wanted to use the hierarchical diagram just to see how these two types, where I created the ordered categories, I wanted to see if the model really detects that they are like redundant. So I look at this hierarchical chart, and that is true. You could see owner type original and owner type as ordered categories. They are absolutely the same. So I know, like, if this was a very important feature, I knew it would be totally fine to get rid of the owner type. But it's gonna fall out of the model anyway because they're not important. What I see here also that mileage and mileage numeric, they are pretty close to each other, but power is pretty far from power. Like power numeric is far from power. Engine numeric is closer to the power numeric than engine to between engine and engine numeric itself. So I think that's properties of the domain. This is where people who understand cars, they will probably know that probably there is a relationship between power and engine, and I am not the person to judge. I'm just looking at the diagram and interpreting the results. RK, do you want to say anything here?
Well, I'm just guessing. Was engine number of cylinders, or was it like a displacement number?
Let me. I can't because this is GitHub. I can't run it, and unfortunately, it doesn't show all the fields. Okay. Let me look because I have it here. Columns. You ask for engine, right?
Yeah.
It's not giving me preview. Why not? So I clicked on it before, and I thought by this time it would download, but
I just say that in general, if engine is a representation of either the number of cylinders or the total displacement of the engine, it would be directly proportional to the power that it produces. It's not a one-to-one. There's obviously noise in that assumption, but they would be very closely related. What strikes me as surprising is how the well, the price didn't have a split. So I'm looking at it, I'm like, okay, well, power had a unit. And so if you had when you turn it to numeric, you're removing that unit.
Yeah.
So, but then you would expect to see the same thing in price when you remove that unit. Did you do a currency conversion on the price numeric?
So the price numeric is actually, there is a field price, which is the car what it's sold for in the used car market, versus new price. And new price is a field that's not really populated. It's a value where they say if this car existed as brand new, this would be the price. So that's the difference between price, okay, which is our target value, and new price is just comparable new price if it's like available at the dealership. Make sense?
Yeah, that makes sense. I was misinterpreting that.
Well, I didn't cover that. Yeah, it's a very good point that new price is a totally different field from price. Yeah, and the power, I think, or the engine, I think what I saw was in cubic, it had like number cc, cubic something, right?
Yeah, that. Yeah, that would be the displacement.
Okay.
CC or CL.
Yeah. All right. So I'm gonna remove the low importance features. So just like in the book, I'm gonna give it a threshold below, like anything below this number to remove it. And we end up with, so the model chooses these fields, which you can see that like all the numeric fields made it, and some of non-numeric stayed, like mileage stayed, and power stayed, engine stayed. Actually, all of them stayed. And after that, I'm gonna rerun the same. And now I'm looking at the model with the picked fields, and you can see the same elbow again. So I'm very happy that there was this field car ID. I'm very happy that it went away because I was gonna get rid of this anyway. Because that's just a sequence number and it doesn't mean anything. But here it again shows us that this is what got picked. And I know that I want to remove redundant features. I know that I created these numeric fields, right? So there's new price and new price numeric, and mileage numeric, and engine numeric, power numeric. So I'm gonna remove them manually. Before I do that, I want to get the R squared, which is our metric for seeing how, this is our baseline metric. So 0.83 is very similar to the book where it's 0.87, and that kind of tells you, R squared tells you how much of the model is captured, like how much features in capture the model. So 0.83 is decent. It's not as good as 0.99, but it's pretty good and comparable to the book. Then we're doing these comparisons. The numbers are very similar. So it tells me I feel comfortable dropping these features where they're non-numeric. Then we create this final model, and that's what it looks like. And partial dependence, that's I'm gonna quickly go over this so I give other people a chance to talk after me. Data leakage we didn't talk about in the lecture, so I'm gonna skip it. Tree interpreter is an awesome diagram. It's where you can look at a specific record and see how that specific record basically influenced by the model. Sorry, like I'm not good at explaining things. I would just point you to the chapter in the book where like it's very well explained, and I'm not gonna do it justice. Jeremy is much better at this. The extrapolation didn't happen here because we didn't have that time series trend, so I didn't do it. I'm very happy that Jeremy taught us how to do it because it's really important. And finally, I'm gonna use a neural network. So I'm gonna do the same pre-processing as I did before. I'm gonna create these numeric values. I'm gonna make sure that I'm using the same fields. And now I'm ready to, I'm verifying that all the values, all the fields are in the right data type, because the model obviously, machine learning obviously prefers numbers, but it can handle non-numbers like object, which is strings, and which become categories. I want to make sure there is no null values after all the conversions. I want to see number of unique values. So here the name is the most high cardinality. So we have 1,800 different names in the data set of 6,000. The rest of them look pretty good, low cardinality. And so this is me just making sure I understand what I'm doing, because in my world, I always look at data types, I always look at shapes, and I always make sure that, you know, things are ready to go. So I also needed to pay attention to this range. So the range of prices is between 0 to 120, and I made sure it happens here. I got this learning rate finder, and it just went down, down, and down. It never started going up. So I just chose this as my learning rate. I played with other rates. I literally set it to 1, and it was doing pretty bad. But this is my training loss and validation loss. So you can, I started with 5 epochs, but it was not doing pretty well. So if you see 5, it goes to like 74. So I increased it to 15. It goes super fast because it's a tiny data set. And training loss keeps going down. Validation loss started going up here. So pretty good number 15, because that's where it's starting to not improve anymore. And this is quite large compared to, remember, like in our random forest, we had a loss of just $5 or $6, and here we have 39. So this kind of proves to me that deep learning is not a very good example for tiny data sets, which is expected, so I'm not surprised. I'm looking at the prediction. So I got the pretty good prediction RMSE, which is 6.25. Oh, sorry, I forgot to include here. This is our ensemble. So ensemble is where I combine our neural network predictions, scoring plus random forest. And together the loss is 6.25, which is much better than 39. So if this was a real deep learning example, we would, you know, I hope we would get a better rate here, and then we could possibly combine this model, neural network model, with the random forest model to stabilize the results. But this is what I've done so far. Oh, sorry. No, I was wrong.
Sorry, question about the numbers. Can you show me the top part where you created the learner?
The learner. Here?
No. Yeah.
Oh,
so
here.
You're using MSE loss.
Yes.
Right. So and then I think you were using RMSE. So
which is a square, which is a root
square root, right?
Yeah. Yeah, I just followed the book. That's like, it's nothing original here. But yeah, I see your point that this is...
The 39 is actually...
Correct. It's a root of 39, right?
So
that is 6.25, yeah. You're right, yeah.
So it's pretty close.
Yeah, it's pretty good. I'm glad you pointed it out, because I was like I was just rushing to make a decent notebook for this. But yeah, you're right. This is this is MSE and this is RMSE, which is 6.25, and our random forest was 4 point something. So the difference is pretty small, which is encouraging. On such a tiny data set, I think this was our 4.77, our best rate. Yeah. So this was our random forest 4.77. This is 6.25 is our neural network. And then I ensemble it together. Sorry, I got confused there and misled you guys. Yeah, I ensemble it together, and together this is the rate, the validation loss. And that looks pretty good, if you ask me.
Question.
Yes.
I have not read this far, but in the book, so question. The ensemble, is that from the book or a technique you're applying?
So ensemble is just averaging. It's from the book. This notebook is based on the clean notebook,
Okay.
but the ensemble we're just averaging between the neural network and between the random forest. So we take two models and we are averaging the results. You see, we're just dividing by 2.
Oh, okay, understood.
Yeah.
So, and I'll give you the context. The reason I asked that, and obviously I didn't read the chapter, but I went to meetups in Austin where there were startups, and there was this particular startup that identified attack vectors for network intrusion, right? I mean, so they would use something we have, let's say in a standard Norton installation or whatever, signatures of the viruses. And then they would track the behavior of people coming in and their behavior, like how they tried to poke into different IP addresses and went to MAC addresses and so on. And their definition of ensemble was not necessarily a straight averaging, which is somewhat what we do in random forest at the result level with multiple trees. But
yeah, random forest itself is an ensemble algorithm. Yes.
Right. So what they'll do is they would use different techniques in sequence, right? So they would use a random forest, they would use a neural network, they would use a linear regression. And the sequence in which they did is also an ensemble. It's more kind of a model pipelining. Right, so.
Correct. Yeah. So ensembling in machine learning means using more than one model.
Yeah.
And
exactly.
random forest itself, because you use 40 trees. I'm trying to look up at Jeremy's definition, but you can all read in the book. Yeah, it's ensembling is beautiful because you can average 2 models or you can average 100 models. It's just it depends how, like, boosting and it's another way, like GBMs, the gradient boosting machines, is another way to ensemble, and it just yeah, ensembling is beautiful. I highly recommend it.
Okay.
Yeah, but so the conclusion is, you know, I'm gonna be like Jeremy. There are 2 approaches: ensemble methods and neural nets. He started with the ensemble just to show how random forest does a really good job, and it gives us a stone baseline, and it's really good for comparison and exploring. So when I did neural net, you see how it compares, and even on this tiny data set, it did pretty well. And you know, then if now I'm ready, now I understand what I'm doing and why am I doing things. Now I'm ready to apply it to really large data set and see how it does. So that's about it. Any questions?
I think one thing I'd like to bring up, just for people's thoughts on it. I guess when you're talking about neural nets and needing, you know, bigger data sets and stuff, that's a particular problem with tabular data sets because we don't have the benefit of doing the augmentation part.
Yes.
You know, with the image, you can augment it and rotate it, and all those things mean something. And like Jeremy even says in his presentation, like augmentation for.
Yeah, like he doesn't know how to augment the tabular.
What's that concept mean?
Exactly, yes.
Yeah.
Yep, I agree.
I was making a few notes. as you went along with the presentation, I'd like to share them.
All right.
Yeah.
I stopped sharing.
No, please keep your notebook on.
Oh.
I may have to request you to scroll up and down. Okay.
I want to give space to other people.
Oh, I'm occupying all the vocal space. So the work and the credit all goes to you. So here's what I found. There's a point in your notebook where you had horizontal bar charts, and you pointed to the engine number and the power number, two variables, and you were thinking of how correlated they are. Yep, right there. It wasn't a bar chart. It was this point. I think it was in a bar chart too. Yeah, so right there.
So this is feature importances
Yes.
versus this is looking for redundant features.
Absolutely. So on that thought, feature importance, right, and narrowing down to the minimal amount of features, in computational learning, one of the theories is the simpler the model, the better it is in the real world. And I don't remember the exact name of that theory, but there are 4 or 5 key tenets for computational learning, which is from where all of our statistical and ML is derived from, right? So it's kind of a branch out from there. But practically speaking, at that point, you could draw a cross-correlation matrix. It does wonders. Essentially, it takes each variable and plots it and does a Pearson correlation. And if the value is, let's say, 0.8 or 0.9, you can very safely knock out one of the variables, right?
Yep.
Because having too many dependent variables or like highly correlated variables create unnecessarily bias, and they are giving redundant information, right?
Yep.
So you can, right? Okay. So
yeah, that's where like here we used R squared, but there's also R squared adjusted, which punishes, the more features it has, it punishes you, the model. So yeah, I think it's called parsimony principle, where the simpler model is the better model if you achieve the same results.
Yep, probably.
Yeah.
Okay.
Yeah.
So
the random forest is quite resilient to that, isn't it? Just because of its
yes,
the selection of a random subset of features at each node to decorrelate.
Yeah, random forest is very good for tabular data. I'm like, after doing this chapter, I'm very happy that that's what I did for my work, because I had to choose between like 7 different algorithms and I chose random forest. So now I feel better about it. Yeah, and random forest, you don't have to scale features because feature scaling matters. And I think there is a normalize somewhere here in
Yulin, were you talking about principal component analysis?
So I do have that.
Or is that different?
That's different.
I do have that as a point, but no, I was not talking about it. I would like to talk about it next. So
yeah, PCA is different. But this is in random forest, we didn't have to normalize because random forest does splits by, each node, it does split. In non-random, non-tree models, you have to normalize. So you have to scale your data so it has the same scale.
yeah, I mean, so I had to so like normalization and scaling, it has its own problem, right? As long as we know when to use it, not only because of the reason that Daniel mentioned, and you were agreeing with Tanya for the algorithm, which may or may not be sensitive to it. What happens is, simple example, right? It can have a disastrous effect on the outliers. There may be a value. So simple example, and if I'm speaking too much, tell me. So some variable has a range from 1 to 10,000. Another variable has a lot of values around 10,000, right? And distribution of variable. The second variable is equally distributed, but is between 1 to 5. Now, when you normalize that, it may not translate in a 0 to 1 scale exactly. Normalization also, and I think scikit-learn does a very good job of explaining the type of normalization techniques or the scaling techniques. Right?
Yeah, and outliers, it's its own topic in
Yeah.
linear modeling and Yeah.
Yes, median model. Yeah, I mean, that gets too much into statistics that the rule of thumb I've used is, instead of thinking about even as a super basic level, for everything where I'm using mean, should I use a median or a mode or some other, complicated form? The rule of thumb I made for myself is I will always keep normalization or a normal curve or a Gaussian curve, right? And that being the most common distribution, but more so, the first thing you do is you take every variable and you draw its distribution curve, period, nothing else, right? And that is also as insightful as looking for missing values or nans and so on. So, right?
Yeah.
Okay. So let's talk about PCA.
So I'm gonna stop sharing. Is it okay?
Actually, no. I insist that you keep it.
Okay, Andy, I need help.
No, this is beautiful. It just happens that I've done about half a dozen things using the same mode, and I've had to vary between different those projects. So I'm quite conversant with the approach you've taken. So let me actually take you to cumulative, the point where you talk feature importance, and then I'll bring PCA into the picture. Go to where you brought feature importance and you listed. Yes, right. This curve, exactly. Right. So, and I don't know why I forgot the reason, but a random forest naturally extracts feature importance. So, in many cases, when you're using something else, just use RF for its feature importance value. And the way to look at it is the cumulative curve, right? So if you look at the bottom upwards, 0.35, 0.2 year transmission, blah, blah, and suddenly you apply the Pareto 80-20 rule and say, guess what? I'm going to cut off everything beyond 80% of the total value being derived or the total accuracy being gotten. You use a slightly different technique, right? I mean, you just cut it off based on some in that single line code you had there. So that's another way of thinking. I've used that Pareto approach. And then what I did was, what I've done before is, like, once I cut it off, like using this random criteria, I rerun the entire pipeline of models, right? To figure out which is giving me better accuracy or not. A, B, which set of features from a domain knowledge wise makes sense. In this case, you're going to RK and asking him, hey, does it make sense from a car's perspective, right?
Yep.
Right? So that's the thing. So that was the thought I had. Let's come to PCA. PCA is very interesting because it's principal component analysis. And I'll start with the problem first to RK's question. This thing is very beautiful, what's there on the on Anya's notebook here, because it tells the variables as they have been captured in real world. What principal component analysis, which is in turn dependent on icon vectors and all, transforms this, and it can give you out of these, let's say, I don't know the exact count, but maybe let's say 15 features she's showing. What it'll do is it will create 4 features total out of it, right? And each feature will be an equation consisting, a linear equation, let's say, consisting of a combination of different variables, right? So, for example, feature 1 may be y equal to 10 times power of number plus 5 times engine number plus 4 times use. That's a 3 variable vector, right? And then the second feature vector could be 4 times transition plus 5 times transmission plus 4 times transmission plus 5 times zeros plus 6 times power, and so on and so forth, right? Now, suddenly, you do not know how to interpret those feature vectors, right? Your accuracy will be phenomenal if you use them, but the translation to an expert, a domain expert, and say, guys, if you modify this feature vector, sorry, what do you mean by that? Should I change the engine, some value in the engine or what, right? So that's a disadvantage. So, but it's very powerful because if you start to think of it, and if these, and they used to say, now they claim they don't say, I don't know much about this, is neural networks, when it comes to explainability of a model versus accuracy are not so good. That's not the case now, right? but 2-3 years ago, they were saying that a lot, right? And random forest was good because you could see each feature being broken out. PCA has that explainability problem. Does that make sense?
Yeah, that makes sense.
Yeah, and we saw PCA in the previous chapter when we were taking the movies and plotting them in the two-dimensional space. That's where we use PCA. We use the two first principal components to plot the data in two-dimensional space.
Okay, I'm sorry, I have not read that section of what you're saying. I'm gonna catch up now.
Yeah, PCA is a wonderful technique. It just, you know, every algorithm has its own purpose.
Yeah.
And like, I'm super happy with this chapter because that's so applicable to implementing models in enterprise settings. Like, you know, for my work, we don't have images of cats to deal with. I mean, I love, you know, I love playing with big pictures, but for my work, it's just not a valuable modeling.
So you're saying you don't use PCA?
No. I'm just saying, like, I'm super happy Jeremy covered tabular models because that's something I can go to work and apply them with deep learning. Because before this chapter, I was using random forest, and now I can actually, you know, I never recommended deep learning before, and now I can say, let me try deep learning and see how it works.
Sorry, one more question. Does your line of work doesn't have any images at all?
No, so I work for a logistics company and we deal with supply chain. So we don't process images. We don't build models with images.
Well, I would say, Anya, just as you're saying that, one thing that struck me, I think it might have been chapter 1, was where he gave examples of people converting graphical and tabular data to images and using a neural net to process that. But I am 100% with you that 99.9% of my data is tabular.
Yep.
Pretty much everything I'm trying to do. The one project that I mentioned to you guys before is literally one of 2 projects that I've ever worked on that was image data.
So I stopped sharing because I want to see you guys.
So to our guest point, I have a trick sort of an idea. It's like, I mean, it's not trick. So people are using multimodal data sets, right? I think Anya mentioned that. She said that you can mix different inputs, so let's say she said supply chain. And in supply chain, the behavior of the individual suppliers and the markets they are in is very important. And you almost want to predict when a supplier will go bankrupt, or because of a weather storm, something could happen to them, or the amount they can produce is going to be less, right? And those tend to be time series prediction or time series forecasting issues too. So now suddenly we could take his idea from the first chapter of, instead of doing time series prediction, taking images of those predictions or the variations and then feeding it as an input to some model sequence along with whatever she's doing, right? So you combine tabular and image data. I mean, it's a weird way, but great.
All right, Andy, I think it's now your turn.
All right, let me share screen. I'm not as advanced as Anya or Daniel there. So there was a chart on page 255 about the movie data set. And he gave this like Excel spreadsheet. And let's see if I have it here. So it was this spreadsheet here, except he's got float values and I've got just the numeric values. And I actually plotted each one so I understood. So he's going over the concept of the embeddings, and I was having a really hard time understanding what this meant. So what he does is he copies these cells here, and he puts it on the bottom here. So it looks like that. So it's the same, let me minimize this here. So it's the same kind of thing he's doing. So he's just copying this, right? This whole sheet, and then he brings it down here. So he's just gonna take this, and then he's gonna put the same values in here. But he's gonna put 5 different ones, and this is what he was talking about, 5 different features. So he doesn't know what features they are. So they're just a random number between 1 and 0. And he just randomizes this. And so these features could be like, is it a new movie? It is a sci-fi. I think one he says, does it have a famous actor in it? And so these are all the features a movie could have, but he doesn't know. So he just randomizes these and puts it on the top of the columns for the movies. So these are the 15 most popular movies. And these are the kind of 15 kind of largest movie watchers. So he made a mention that you can see that in this set here is like, here's 3 people that watched every single 15 popular movie. But as you see here, there's like a space here, right? And this is what he says your model wants to predict. So like in the case of Daniel's presentation, he had a 0 here, and Jeremy uses a 0 to fill in these values. So a 0, you know, you can't have a rating of 0. You either have a rating of like 1 or 0.5 or something. So I think the data set having 0, you need to be careful. And just looking at this Excel spreadsheet and just hearing what Daniel had to say tonight, it's clear that these null values that we want to predict is not 0.
But I do think that that was a different situation, but point well taken nonetheless.
Yeah.
I think that they were trying to interpolate situations where people like did read the book but didn't leave a rating to try to get information from that. Like
yeah.
there were still combinations of users and book IDs that just had nothing in them.
Yeah. So, you know, if these were 0, then, you know, you would have to say, then it's something else, right? But since there's blank, we're assuming that the values are 1 through 5. So that's kind of what he did with these feature sets, is he's just saying, is it a new movie? Is it a sci-fi blockbuster? He doesn't know what these are, but he's just saying, if these movies had features, here's what we could plot, right? And then he does the same thing with the users. So this might be, this is watch a lot of movies. Do you watch it on Netflix, or do you in a theater? Are you social? Are you a big influencer? And maybe your income. But again, he doesn't know what these are. He just, you know, just puts these just kind of like, okay, let's just make some random stuff up. So then he does the same thing. He gets random 0 to 1. And what he'll do is he'll plot this same graph here so that you have something like that looks like that, right? And then what he's going to do is something interesting, is he's going to use this matrix multiply, and he's going to multiply using this value. He's going to multiply this and this, and he's going to come up with a number. And maybe I can do it here. I take this and copy it. Hopefully this works. And if I go like equals, and then he just applies it to the whole thing. Oh, first that, and that. So he comes up with all these values, right? Doing a dot matrix multiply against random, you know, he doesn't know what these features are, but then he just goes with randomness here, right? Trying to predict. You can see that if I click on one of these, click on this, you can see he's doing this and this, right? So that's kind of what he's doing. And then he says, okay, so now that we have that, why don't we try to get the square root of this chart and this chart? and he gets this square root formula. Let's see if I put it here. Ah, I did it. I can put it here. Sorry. I'll just put it here. It's not going. So if you look at what he's done here is, oops, he's taken this, the known values and unknown values, and he's done this sum, you know, of both, and he's come up with this number. And then he uses this solver tool. I don't know if you guys know how to use it, but I can't see in my little thing. It's in data, this solver. I don't know if you've ever used this thing. So if you look at solver, it basically can do a min, and it has this formula that you can get the sort objective, which was that, right? And you want to get the minimum. And then you just basically say, give me all the values between these random numbers and then these random numbers, and give me the correct weights. And so what he, after running solver, so what he's doing when he gets up to this thing, and he calculates all these values, is he's just done the gradient descent of all these numbers here. And he ends up with this nice notebook that looks like that. And this is like the solver number that he comes up with. And what's interesting is, you know, these numbers that he gets is 0, which you didn't have, right? But he wants to see, is this number close to this number, to the predicted number, and this number to this predicted number. So what I did was I just copied his formula and ran this solver. And this is the same number he's getting in his notebook when he runs the solver piece. But in this one, he adds, oops, wrong sheet. In this one, he adds these weights right here, which is just another column of random values. And this bias, again, this row of random numbers. And then he adds them together. So let me see if I have it here. So you can see he's taking this and taking that, and he does that cross multiply, and then he adds the two, and he finally gets up with this number. So what he's doing is he's showing you in Excel how to build the first pieces of that embedding. So where he says this is 5, in the book, he will go 50. So what's interesting is he's predicting movies he's never seen with users he's never met through that model. And then he uses, you know, in the notebook, you'll see he's using stochastic gradient. So stochastic gradient isn't gradient descent. Gradient descent is doing this, but stochastic is doing it in batches, right? So that's what he says. So it's even a better model to figure out the loss, but he comes very close at predicting, just on these random values, the types of movies that a user would watch based on the pattern that he's inputted before, which I thought was kind of neat, because here he's showing you that these numbers here, he just pulled out of thin air. He just did a rand n, right? And then he just said, okay, let's just take these numbers and dot matrix multiply this. And he comes out with this very close model without even running it through a neural net. And then you'll notice in the notebook, he's showing you some of this, but he doesn't actually walk you through this. And what's interesting is this whole discussion is in a YouTube video by him on December 20th, 2016, when he was talking about this whole thing in deep learning for lesson 4. And it's at 143. So he walks through this whole Excel spreadsheet. So I really got into it, and I copied the exact same values to make sure I understood what he's doing and how to use this crazy solver thing, which maybe some of you guys use, but I've never used it before. But I got my first experience in Excel doing neural net, kind of playing around with that. And I also noticed that, you know, when he puts it into the deep learning, what he'll do is he'll take these values, right? And like the other one where he stacks it on top of each other, he'll stack these end to end. So instead of, like, remember on the image, what was that, MNIST set, we were passing in 784 pixels. So you can imagine this is like 50 and 50. And so he's passing in like that 100 piece in there, and that's that first set of inputs. And that's what he was talking about in that movie lens piece. So my question is, these factors here that he's saying, not this one, this is the bias, but these factors here that he's saying, is this the embedding, or these are just the factors he's just coming up with? Because I thought embeddings make it smaller. You know, because he went through, you know, what's one hot encoding, and, you know, explain the difference. But you can't use one hot encoding with this because there's multiple values here. So you would have like 1, 1, 1, 0. So you need to use some other method. So he uses encoding or something, and you get a value. But you can shrink it down to one embedding layer value. So I'm still not understanding, is this the embedding part, you know, these values here, or are these just, you know, because he uses a different embedding value. He doesn't use 50, I thought. Anyways, that's all I kind of was playing around with before I got stuck with Colab on the tabular data set.
Andy, in my mind, I was thinking, because of the way he described those, the value, so you have the 0.99 and then the values under that, so under the bias, I was thinking, because of the way he described those were more like model features. And that is the weight of the feature that it represents. Now, when he talks about it in terms of, you know, this is like, was there a popular actor in the movie, or was there, you had that over to the right, you had like kind of examples of things it could be. Yeah, like new movie, sci-fi, blockbuster. And so I think of these as the weights of the features. But right. In this case, I know he gave singular examples, but to me, it seems like this is almost a PCA representation of the weights, because to have only 5 things, you don't know what they are. So they're most likely going to be combinations of factors, like what was explained earlier, that are representing something that helps the model decide what it should be.
Yeah. And that's interesting, because he says that you don't need to know these. It's just, how many of these do you want? And so you just say, I want 50 of these, or 20 of these, or 40 of these. And then you let the model tell you what the proper weights are based on these, you know, targets.
Yeah. And it's exactly to Yulin's point that is where you lose your explainability. Because we don't even care. In some sense, we don't care at this point what they are. Like, just let them be whatever they need to be and see if the model works. But we all know that there's a lot of unintended consequences when that's the case too.
So I'm not sure, like, okay, so how does he know to pick 50? That was my next question. Like, okay, so you have this data set of 1 million movies and 1 million users. What is the this, right? How do you just say n factors of 1,000.
Well, I mean, if you had some experience in the field that you were trying to do that for, but I think he just chose what he chose. I don't think there was any analysis saying that choose 50 or whatever. But I think like Anya's example, when you look at that bar chart and you see how quickly the random forest doesn't need half of the features that you're putting in there, you know, you can get a feel for where the cutoff needs to be. I mean, this is kind of a hybrid thing that's not exactly the same, but that's what I'm thinking is that, you know, that if you had 20 features, 10 features are going to capture 98% of of what the model needs.
And I think the weight decay would contribute to that as well, encouraging a lot of the weights to be small.
The other thing I think, Andy, is that it kind of mentions that there's this function in the Fast.ai. I think Daniel showed it, the get embedding size, which is like a heuristic kind of thing, but he came up with that just by running a lot of experiments. So it's based more on experience, not on a theoretical thing. So it's like after running, I think, running it on a lot of data sets, he, I think, came up with this exactly using the random forest by collecting a lot of data and then coming up with like a heuristic that was usable for a lot of data sets. So it's not like there's a theoretical basis for it. It's more like based on experience by collecting a lot of data, running varied, like essentially something like a grid search. Yeah, basically like running, what if I use 50? What if I use 100? And something like that, collecting it over time. And then basically, I think they ran something called, they used random forest. I know that because I remember that discussion to come up with like just a heuristic, which they embed in this get embedded size function, which I think Daniel showed in his notebook.
I just pulled up the code and it says, rule of thumb is through trial and error, this general rule takes the lower of two values, a dimension space of 600, so that's why mine capped out at 600, or a dimension space equal to 1.6 times the cardinality of the variable to 0.2 or to 0.56.
So I think, yeah, that's basically a heuristic that they came out with. I think coming out of a random forest, running it on a lot of their data results. So again, there's nothing like magic about it, except it's like, why do they use 1 minus e to the minus 3 for the default for like their learning rate? Again, it's like based on the experience that they have, and they found these to be the useful defaults. But you don't have to like use it. Just, I guess, if you're deep into a particular domain, you kind of want to experiment. And I think the other point about what you're asking is if the embedding is the numbers and how they come up with the what do you call this? The relationship to the one-hot encoding. I think the idea is that the embedding is exactly these, the numbers that you come up with, the weights. But the way they're doing it is, if you take a look at the code, I don't have it with me, but Daniel, the original, if you go back to the original notebook, where he starts using this object called nn.embedding. It's basically a lookup table. So your user number, I think, I don't know. So if you have the original notebook, the way I think about it is the embedding is like a lookup table.
Let's see. It's
Don't have the notebook. I can't share it with you because I don't have the notebook either. But the embedding contains like is basically something like a one-hot encoding. So you give it something like the user ID or the movie ID, and it looks up this row in that embedding that has the 7 or the 50 weights that are randomized. So if you go back to the start of definition of the model, the dot product model, I think this is at the start, at the top, where you build the model, the dot matrix, the dot product model, because that's, creating the latent factor. I think it's called the latent factors.
Okay, this one.
There's this cell where they create the collab filtering from scratch, I think, where he's using the collab filter from scratch, the next section, I think. Because that's where he introduces the concept of embeddings. Yeah, that one. There. So the embeddings is like a matrix that you use for looking up. So user factors is the number of users. So I'm going to have one row for each user. So it's like one hot encoding, except it's going to come up with n factors. So there's going to be 50 random numbers there.
Right.
But rather than actually build an actual matrix, the reason why you're using embeddings is because it's going to be more memory compact to use an embedding. So if you go down the forward, take a look. Users times movies times sum. So users is the like the 50 random numbers for one particular user. So X, the first statement in the forward is grabbing the users for your batch. So if I had 50 users, I'm gonna grab the 50 rows for those 50 users, one for each. And then in the movies, I'm gonna grab the whatever movies I have in my input and grab them and then have them multiply each other.
Okay. Yeah.
So
just my
the
question
way
was,
to think about embedding is it's like a combination of one hot encoding to look up a row in the. So it's like if user factor and then you index it with 1, it's gonna be the embeddings for that particular user. It's gonna be the 50 numbers, which we start out with random digits. So it's exactly like the looking up the row for a particular in the Excel spreadsheet. It's specifying the set of values. In the Excel spreadsheet, you're using the 5 values, right?
Yeah. I just was confused on how he selected this 50. If it was just.
Oh, there's a you basically there's I think there's mention called get embedding size, and I know there was a discussion during the lectures as well about that. How do you come up with that? And basically they said, well, it's a heuristic we came up with.
Yeah.
So there's nothing magical about it. I guess if you're deep into a particular domain like Netflix, I guess, or somebody who's like using it all the time, you'd probably know what the good size would be.
See, it's right here, right?
Yep.
So
but there's
that's why I said, how did he get this 50? I'm just running it and I don't know,
there's a method called
60 good, 70 good, or
no, this is for the random. Down below you'll see there's a get embedding size. get embed size or something.
Wasn't weight decay, right?
Yeah, I think in general, this kind of gets to the questions that I brought up about what general processes there are for hyperparameter tuning.
Yeah.
Yeah. Well, yeah, definitely not the expert on this.
Okay. So that ended my little fun thing there.
Thank you. I really liked seeing that step-by-step in the crosstabs. I thought that was really interesting.
He does a much better job there, but I just thought it was amazing that, you know, he was just doing this all in Excel first, and I could see then how he moves it from Excel to here. And now I can see what he's doing, right? I understand a little bit better. And actually, I didn't watch the whole video, but I'm thinking he's doing the whole thing, the explanation of all the different things that we were learning in Excel first and explaining all the processes in Excel. So I don't know if I would watch it again versus watching video 8.
Can you include a link to that Excel, the one where he goes through from 2016 with a timestamp?
He doesn't have it. I had to create it myself. But
Oh no!
I meant the YouTube video.
I remember there was in the 2019 course. There's a link to those Excel spreadsheets. Yeah, it's kind of like, yeah, it's not easy to find, but I remember saving it away for some reason.
I didn't.
Unfortunately, it only runs in Excel. So if you don't have Excel,
yeah, I actually did find one, and it looks like his, but the movies one that I just showed you is not there, and it goes through all the different optimizers like Atom and stuff like that. And I'm assuming he's talking through each one of those, you know, like the SGD and Atom and all the optimizers, and walking you through the Excel. So I found that one, and I can put it up somewhere, put it up on the GitHub site, I guess. And I can put up the one I did, but it's kind of interesting to watch that. And then he just does gradient descent using that solver function, which I thought was kind of neat to watch it spin a little bit.
So I have a question. I mean, that spreadsheet in your walkthrough was very cool. I think it was the way you stepped through it, kind of explained. I still don't understand how the distance between the randomly generated numbers and the final thing that he minimizes as an objective function. I mean, how that works, I can't picture. But I have a question. So in that solver thing in Excel, I've not used that before. The thing about neural networks is the backward propagation, right? You go through it once and you adjust the weights at every node, right? The W values. And suppose the activation function, everything remains constant, and now you back propagate and you move back and forth, right? And you fully adjust all the weights, and boom, this is minimum loss, highest accuracy thing, right? How does that solver work? Does it actually, do you see waves of numbers changing, going back and forth or something?
I think it pushes like all the possible values at once, and then does it again, twice, 3, 5. Because I see my thing, it goes like 150, 200 times in my little Excel thing. And I think it's passing all the values, and then in the end, it figures out which is the lowest one and chooses that. Because, well, let me see. Can I
I think it works the same. Do you see the what if analysis tab up to the right? You see next to forecast in the forecast tab, further to the right.
In the ribbon.
Yep, little left. If you click that drop down, there's the goal seek. I use that all the time. And the solver is an extension, I believe, of the goal seek. The goal seek is just one cell controlling another one.
Yeah.
So it's like a straight up Newton-Raphson quadratic convergence model. And I think what the solver does is it allows you to have multiple input cells. Whereas goal seek, I mean, you can click on goal seek, you can see that there's only 2 inputs.
Yeah.
So you set this cell, you want the value to be 0 by changing some other cell, and the solver lets you set up an array of cells instead. But this just uses a Newton-Raphson optimization.
Basically.
Yeah, you'll have to watch the video and watch him do the solver, but I think the whole point is he's doing, the Excel is doing gradient descent and is trying and picks the best one out of all the trials that it did. So I don't think it's trying to figure out the back propagation. I think it's just running all the possible values it can and then picks the lowest one. And then ours, you know, we actually run the model and then make adjustments to those weights. So our model gets better and better through that back propagation. So that's how we do ours. So normally we should be able to beat, you know, the Excel one coming out of there. But it was a nice exercise.
Yeah, the Newton-Raphson was described, I think, in chapter 1 when he first started talking about gradient descent, where you're on the side of a mountain and you take a little step in one direction.
Yes.
And did it get better or worse? The multi-dimensional extension of that is for each position you're in, you take a step in each of those dimensions, whether you have 5 or 50, and then you take the gradient of steepest descent.
Oh. I didn't quite remember the Newton-Raphson term, so thank you for the recall.
Yeah, I mean, it's just walking down the slope to find a minimum.
Sure.
Is all it is. It's what my master's research was on, so it's all.
Oh.
I mean, in 2001, you know, before neural nets were popular.
No, I have this very funny thought, and it's just connecting dots from what we are talking today, and maybe it's totally random. I wrote a question for myself. Maybe if I have time, I'll investigate. But when you were saying PCA, right? And what solver is doing, and so number 2, and then neural networks. Each layer of a neural network, right? And if you look at those picturization of neural networks, and Jeremy mentioned that in an earlier graph, and I ended up watching that 3M video, 3 blue, 1 brown video, whatever. My point is that, is it possible, this is super random, maybe too audacious, but each of those layers and the things that are assigned is like a PCA, which is adding more and more information as the full image is getting formed through the network, right? It's random. It's more philosophy than practice, I think. I leave it at that. So.
All right, everyone. If we don't have any more questions, and thank you for those presentations by Anya.
I do want to point out one thing that I found.
All right.
In the chapter 9 notebook, it says that it talks about the paper entity embeddings of categorical variables. And they worked on the Rossmann sales competition on Kaggle. And he says that there's an online only chapter on the book's website where he shows how to replicate that from scratch. And I was looking around trying to find it, and I think I found a prototype of that notebook that he says he replicated it. So if you guys are interested, I can share that.
That'd be great. I was also looking for that and I couldn't find it. So definitely send around the link.
Like half of it doesn't have any commentary, but all the code is there.
And can we add it to our Git repo?
Yep,
so we
sure.
can find it later?
Yeah, I'll send you the link.
Because this week is gonna be about the next chapter.
I heard you all say our Git. Do we have a common Git page? Sorry, did I miss it?
Yes, Daniel created one.
Yeah,
Ah,
I'll if you scroll up a little bit in the Slack, you can find it, or I'll add a couple of updates based on this and resend the link.
Thank
But
you.
yeah, feel free to, you know, fork it, make pull requests, what have you.
Sure. Thank you for
Yeah,
doing
and share your whatever Excel files is or as welcome as notebooks, everything.
Sure. Sure.
I have a question about gradient descent, actually. I'm not sure if you guys have an answer, but I was also watching that 3 brown, 1 blue.
Yeah.
That was really amazing. I'm glad you guys shared it. And so I think Anya shared something close to this. I recreated it with my, state-of-the-art Microsoft Paint. But if you're starting here, and it was kind of with the learning rate finder where we were talking about it, if you're starting here and then you end up in this well, right? And you'd think from like the gradient descent, you'd want to be at the lowest point, right? But wouldn't this be overtraining probably? Like if you maximize, like if you had like a quantum computer and you could grade the whole curve, if you took the lowest point in the curve, you'd probably be overtraining, right? Like,
But gradient descent doesn't deal with this. It uses it only works with convex shape, so it has to be the smooth curve with the lowest point. So here it's a different.
okay, well, I'm sorry I recreated it wrong, but like the similar thing where one dips low, like it doesn't go as far as the other, right? I mean, you had an image.
So
From the viewpoint of like the data that you have, if this is the real picture of like what the minimum, because the lower it is, what it means is it's the point where if you think about the model is just a function, right? So you give it an input and it's the most correct one for all your data. So the reason why you split it out to like the test and validations is so that it tries to predict what the real picture is by saying, I'm not going to be training on the real picture. I'm going to be training it on the small picture, but I'm going to check to see if the picture that I have on my training data matches what my estimate for the real picture is. So I guess from the viewpoint of like looking for the lowest point, the lower you are, the better it is, right?
Mm-hmm.
This is what the real picture is supposed to like look like. And it's just that to get there, you have to jump out of that well and go down lower.
Yeah, but do you remember there was a section on that video? You don't know where you're starting, and that's why you can start in random. Yeah, it's many different places. So although you are stuck in that red one, you might be coming down on the other side of the big one, and then so you don't know where you are, but you're just stepping in the right direction of getting a better result.
And the reason
you compare all that, right? Just I think the video does a better job of what I'm trying to.
The other thing I think is because it's a n-dimensional map. It's not really two-dimensional things. It's like all these multiple dimensions. What I think they found was, in general, it's more like they're shallow. It's not exactly convex. So it's not guaranteed. SGD isn't guaranteed to get you to the lowest point.
Correct.
But most of the time, it's good enough to because there's a lot of what they call this shallow stuff that where if you use too small linear what do you call it, a learning rate that's too small, you're probably gonna get to a local maxima. But if you have a high learning rate, it's gonna not find the lowest point. So that's why the intuition for changing the learning rate as you're training makes sense, because you might want it to change fast if the what do you call this? The slope is I'm trying to remember if it was the other way around or one way. But if the slope, if you're checking that after like several steps, the slope was like flat, you'd probably want to like increase the learning rate. But if, no, I'm not sure. But anyway, the idea is if you're finding that the slope is different for like different learning rates might make sense for, if you're getting to the flat area where it's probably close to the local minimum, you might want to decrease your learning rate. But if you're like increasing, like your slope is steep, you might want to jump around like large steps.
Sure.
And that's like,
Cliff, I don't like the one you have drawn.
Okay.
That
Sure.
you're in. Only because from my view, it looks like it's non-functional.
Sure.
So your thing is actually not even a slope down, it's a slope backwards in X. So,
Okay.
But think about it like this. If you were on that first downward slope, say you started at where your drawing starts on the far left,
Okay.
and you were to calculate the gradient of that slope and the broader slope, because it's got kind of a weird shape to it too. But if you were to take a very small learning rate, you would very slowly walk down this and settle at the bottom, like what Butch is talking about. And that's where it would end. It wouldn't get any better because as it tried to go over. But if your learning rate was slightly bigger, you could actually jump out of that droopy thing and over to the next one.
Sure.
And then if your learning rate was big enough on this one, if it was more of an angle positive,
right,
and your learning rate was big enough, you would jump out of these little tiny undulations that you get stuck in.
But
Right,
I guess
because-
my question though is it like if you got to the minimum, would you be at overtraining?
So I think I can maybe get at that a little bit, which is to say that it's not really about gradient descent, it's about the choice of your loss function. So gradient descent is just the optimizer that we're going to apply to our loss function. We typically pick a loss function to try to get some kind of trade-off between accuracy and generalization. So we're not, for example, making a model. If we have a data set with like 100 observations, we're not typically choosing a model with 100 features and then trying to get like the closest possible match to each and every single observation. We're usually trying to minimize like mean squared error or something like that, which is a little bit more general. It's not, I'm not explaining this super well, but it's more about the choice of the function that we're trying to minimize than about the optimizer that we're using to minimize it. So if we're choosing a good function to minimize, which achieves that trade-off between generalization and accuracy, we're going to be in good shape.
Okay, guys, we're already 5 minutes over. Thanks for this great question, Cliff. You're going to have to lead off with the next presentation and explain gradient descent to us.
Yeah, sorry for my drawing. I was just
no. It's actually perfect. It's a discussion out there. I'm sure you'll find very good answers.
Yeah. So
it's just not from us, not from me.
Next week we're going to meet. That will be our last lesson in the video lecture. Please do something and then present whatever you find, whether it's Excel or, just some little piece, just so, you share your knowledge. And I think that's the benefit of, all coming together and sharing different pieces because we're all learning together. So we look forward for Cliff's presentation and you, Lind, and maybe Sophia, the last final push. All right, guys, you have a good